This is the Unit 2 Lesson 6 video. We are in Chapter 5, Section 7 of the textbook, and we're talking about roots and zeros. We've got two content standards again for this lesson. The first one says we're going to need to know the fundamental theorem of algebra and show that it's true for quadratic polynomials. And the second one is identify zeros of polynomials when suitable factorizations are available and use the zeros to construct a rough graph of the function defined by the polynomial. Our mathematical practice is attending to precision. So in the past, we've used complex numbers to describe solutions of quadratic equations, and in this lesson we're going to determine the number and the type of roots for a polynomial equation, and then find the zeros of the polynomial equation. So here's a big old concept on zeros, roots, factors, and intercepts. So let's read through this. It says p of x is some polynomial function, and the following statements are equivalent. They mean the same thing. C could be a zero, it could be a root, it could be a solution. X minus c is a factor, and if c is also a real number, then c comma 0 is an x-intercept. So all of these things are different ways of saying the exact same concept. So if we look at an example real quick, if we have the polynomial p of x, x to the fourth plus 2x cubed minus 7x squared minus 8x plus 12, we can find the zeros of that. The zeros are also the roots, which we can also express as factors if we put them in the form of x minus the root. And they're also the x-intercepts if we write them as coordinate points with y values of 0. The fundamental theorem of algebra, this is a key concept. This says that every polynomial equation with degree greater than 0 has at least one root in the set of complex numbers. This just means that every equation has at least one root, one answer. It might be an imaginary number, it might be a real number, but there's always at least one answer. So example 1, we have the problem. It says solve x squared plus 2x minus 48 equals 0. State the number and the type of roots. And this goes back to something we did in Unit 1. We can figure this out by doing the discriminant. But at least doing the discriminant will tell us the type of roots and the number of roots. But if we want to find what they actually are, obviously here we went ahead and factored. This factors into x plus 8 times x minus 6. You solve each of those equations, you're going to get negative 8 and 6. Those are both real numbers, so there are two roots, and they are real roots. There we go. All right, part B, we have y to the fourth power minus 256 equals 0. Let's try to solve that. So the first thing we're going to do here is we notice that this is a difference of squares. Y to the fourth can be written as y squared squared. Let me write that up here. Y squared squared. And 256 is the number 16 squared. So we have something squared minus something squared. That's a difference of squares. It factors into the first thing plus the second thing times the first thing minus the second thing, which is what we have right here. And this second expression, y squared minus 16, is another difference of squares. 4 squared gives us 16, so this is y plus 4 times y minus 4. This thing becomes these two factors right here. So we now have 3 factors equals 0. So we're going to be able to find at least 3 zeros from this. So if we solve each equation, the easy ones, we would get -4 and +4. Y squared plus 16 equals 0. If you bring the 16 to the right side and then square root, you're going to get plus or minus 4i. So there's 4 total solutions to this problem. And obviously 2 of them are real numbers and 2 of them are imaginary numbers. All right, some check your progress stuff. Pause the video when you have your answer, go on to the next slide. The answer to part A, there are 2 real roots, and they are -3 and 4, choice A. Part B, pause the video when you have your answer, go on to the next slide. And our answer this time, there's 2 real roots, there's 2 imaginary roots. The real ones are -3 and 3, the imaginary are 3i and -3i. All right, this is a corollary to the fundamental theorem of algebra. A corollary just means once you know the fundamental theorem of algebra is true, here's another concept that's true, and it's true because we know the fundamental theorem of algebra is already true. It's like a sub-point. So this corollary here, it just says a polynomial equation of degree n has n roots. So if we have a 3rd degree polynomial, there will be 3 roots. If 4th degree, 4 roots, 4 roots, 5th degree, 5 roots. However, whatever the highest power is, whatever the degree is, that's how many roots they're going to be. Some of them might be real, some of them might be imaginary, but there's always going to be that many total roots in the end. Here we have another concept. It's called Descartes' rule of signs. This is a French word. It's just Descartes. You don't pronounce either of these S's. So we've got a polynomial with real coefficients, and then there's 2 statements that are true. The first one says the number of positive zeros of the polynomial is the same as the number of changes in sign of the coefficients of the terms. So if this changes, if there's 2 terms in here that change signs, like it goes positive, one term's positive, the next term's negative, and then another term goes back to positive, that's 2 sign changes, then there would be 2 positive zeros. And the number of negative real zeros is the same as the number of changes in sign of the coefficients for p of -x. So you would dump -x in every single term and see what happens. This might be a helpful rule for you guys. I don't really remember learning this when I was in high school, so it's probably not super important, but it might help you a little bit here and there. Our example 2, we're going to apply that Descartes' rule. It says we need to state the possible number of positive zeros, negative real zeros, and imaginary zeros for this polynomial p of x. So we know it's 6th degree, so there's going to be 6 total zeros. If we look at p of x, the first one goes from negative to positive, then it goes from positive 4x to negative 2x, and then it's the rest of the terms are negative. They don't change sign. So we change sign here, we change sign here. 2 sign changes means 2 positive real zeros. Or maybe there are no real zeros. If we go back and read the rule, it said there's either 2 or it's decreased by an even number if it's not 2. To do negative x, we're going to plug in negative x in each term. Negative x to the 6th is just x to the 6th. Negative x to the 3rd is negative x to the 3rd, so this sign changes. This sign did not overall change. This sign right here did not change in the end. This sign did. Negative x became a positive. So we're looking at negative to negative, no change. Negative to negative, no change. Negative to positive, yes, change. Positive to negative, yes, changed again. So there could be 2 negative real zeros, or there will be none, 0 negative real zeros. And we're going to make a chart of all the possible combinations. So if there are 2 positive real zeros, and if there are 2 negative real zeros, then there would have to be 2 imaginary zeros to give us a total of 6. If there are no positive, but 2 real, there would have to be 4 imaginaries. If there were 2 positive and no negatives, there would have to be 4 imaginaries. And if there were no positives and no negatives, then there would have to be 6 imaginaries. So there's 4 possible combinations that you could have for the answers. And basically we're saying here we're not going to find out what they are, we're just saying what could they be. All right, our check our progress problem. For example 2, we're going to find the number of positive real zeros, negative real zeros, and imaginary zeros for this polynomial function. Pause the video as long as you need. When you have your answer, go on to the next slide. All right, this is choice D. There's either 2 or 0 positives, there's either 2 or 0 negatives, which means that there could be 6, 4, or 2 imaginaries. Pretty much the same as the example that we just looked at. All right, here's where we get into actually doing stuff that you're going to frequently be doing for this lesson. In this one, we're going to be using synthetic substitution or synthetic division to find the zeros. And we need to find all the zeros of this function x cubed minus x squared plus 2x plus 4. So we know that this is third degree, and because of that we know it has 3 zeros. So first thing we're going to do is try to find the number of possible positive real zeros and negative real zeros. We're going to look for those. So the first thing is, if we just look at the signs, positive to negative, that change sign, negative to positive, that change sign, positive to positive, no change. So there could be 2 positive, or there could be 0 positive. When we throw in negative x, we get negative, 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 positive, no change, no change, no change, no, negative to negative, no change, negative to negative, no change, negative to positive, yes, change. So there's 1 negative real zero. So it says to find the zeros, list some possibilities and eliminate those that are not zeros. Use synthetic substitution to find f of a for several values of a. So what they did here is they're trying different negative values. We know there's 1 negative real zero up here, so we're just trying different negative numbers. And then the blue is the coefficients from the original problem, and this lighter color down here is the synthetic division answer. You'll notice each time over here, negative 38, negative 12, and 0, these are our remainders. When you get a remainder of 0, that means that the number was a 0 or a solution or a root. So negative 1, this is our answer for the negative real 0. So then what we're going to do is, this stuff's all crazy. When we take out that negative 1, let me go back to the previous slide. We'll be left with the second degree polynomial x squared minus 2x plus 4. So that polynomial, we could try to do factorization on it. We could try synthetic division again. But the quickest way here would probably just be to do the quadratic formula. So you remember the quadratic formula from previous unit 1. We're going to plug in the numbers. 1 is A, negative 2 is B, 4 is C. Plug them in here, simplify all this, and see what we get. When we get to the next slide, we see 2 plus or minus square root of negative 12 over 2. We can break down negative 12 like this. It simplifies to 2i root 3. We're going to divide each of these terms by 2. We get 1 plus or minus I root 3. So